So we had the thing with Neva, and she knocked the thing out, and the egg just stayed there on top. And that's because it has inertia. If something is at rest, it tends to stay at rest. You have to push it in order to make it accelerate, right? And so it kind of wants to stay there. That's why, have you ever like pulled a tablecloth out from under a plate or something? Yeah? We can do it right now. Let's do it with this guy. With these cameras. If I pull this paper really fast, what's going to happen to the penguin? I don't know if I can do this actually. He's pretty light. Let's try it. Ready? Come on, I want to clap for that. Why did he stay there? Why didn't he just go off?
Inertia.
Say that again.
Inertia.
Inertia. Everybody say it, because he has inertia. Yeah. What kind of things have inertia?
All matter.
Well, I don't know if love has inertia, but matter has inertia, yes. All matter has inertia. If it has mass, it has inertia. Okay. So if he's at rest, he kind of wants to stay at rest. He will tend to stay at rest. So if you pull something up from under him, he doesn't just go along, right? It takes a force to accelerate him away. What do you think happened here? Something not good, right? These two trucks, I can tell you, were driving on a straight road. Discuss amongst yourselves. Tell the person beside you what you think happened here. Anybody willing to give it a try? What do you think happened? Are they driving the same direction or opposite directions? They're driving opposite directions, right? How did this guy, if he's driving straight, this white truck, how did his trailer end up sideways like that? What do you think? Ava.
He was making a turn.
Okay, that's a good guess. He actually wasn't making a turn, but he was trying to stop. Now, if you know a truck, the braking is mostly in the front of the truck. Okay. So put your hand like this in the air. This is the truck, and this is the trailer. Put the trailer on. If you're driving along and the front of the truck stops, what happens to the trailer? It kind of wants to keep going, right? And the road here is kind of slippery, so the trailer is coming at you, and then he tries to stop, but the trailer has inertia, so it wants to keep going, so it goes like this, and it's swung out into the road, and this poor guy drove right into him. And that's all because of inertia. Here's how Newton kind of said it. An object's motion will stay the same unless an outside force is applied to it. It's a little bit simpler than he said it, but it's pretty much the same intent. This is Newton's first law, and we call this the law of inertia. And all matter has that inertia. So, tell me, let's pretend we're in an airplane. Okay, we're all flying somewhere nice with a beach. And we're flying along at 1,000 kilometers an hour. constant velocity. Answer me 2 questions. Talk to the person beside you and decide, is the plane accelerating, and are there forces acting on the plane, and which forces? Go ahead. Okay, first of all, what do you think if the plane's flying along constant velocity? Is it accelerating?
No.
No. 0 acceleration. How does Keon know that? We're moving, aren't we accelerating if we're moving? No, Bahar is shaking her head. What does it mean to accelerate? What would the plane have to do?
Get faster and faster.
Yeah, we have to change velocity, get faster, get slower, right? So if we're flying at a constant velocity, we have no acceleration. So, are there forces acting on the plane? Yes? What force do you know is acting on the plane?
Gravity.
Good. Which direction does gravity pull? Down. Okay, but if gravity is pulling down and the plane is not falling, like we're just going constant velocity, we're not falling, we're not going up, what must there also be? Okay, so some kind of force has to be acting up, right? So if gravity's pulling down, something has to be pulling up. We call this lift. It's the force of the wings holding you up in the air. And I'll teach you how that works. I'll show you. What would you say about the force of gravity and the force of lift? Good. They gotta be equal. What if the lift force was bigger than gravity? Good, Addison. Then it would accelerate upwards. What if the lift was less than gravity? Then you're going to fall, right? We can draw that with something called a free body diagram. Everyone say free body diagram. A free body diagram, or an FBD, you just draw a box. You don't draw out the plane because the physicist is really lazy. So we just draw a square. And we say gravity goes down. We say Fg. And we could call this F lift, upward. If we're flying along, is there a force pushing us forward? Devan says yes. We could call that maybe thrust or applied force. We'll call it thrust of the engine. So that's pushing us ahead. If there was no air, what would the plane be doing right now? Would it be going constant or getting faster?
Getting faster.
It would be getting faster because we'd have this force and there'd be nothing slowing us down, right? In our plane, as we're flying to Indonesia or whatever, we're flying along at the same speed, so the plane is pushing us, but we're going constant velocity. So what am I missing?
Air resistance.
Good. We have to have something pushing back. Otherwise, we would be getting faster, right? And these two forces also have to be the same. So we could say these two are the same, and these two are the same. And we would call this, I could call this force of friction because the air is kind of producing friction against us. Because these two are balanced and those two are balanced, that means that my net force, the overall sum of all the forces, is 0. We would say F net equals 0. And because of that, we would say the acceleration is 0. And we know it's 0 because we have constant velocity, we're not changing. Okay.
My
but it's still moving, so shouldn't the air resistance be less than the thrust?
Great question. He said right on cue, if it's still moving, the pushing force must be greater than the resistance, right? Junior is like, no. So this is the intuitive thing you have to get over. The quick misconception is that if you're moving, there has to be a force pushing you forwards. But there doesn't. When I was a little kid, us humans, we made this thing and we flicked it into space. It was called the Voyager spacecraft. We wanted to get a look at the planets, and so we launched this thing into space. That was when I was little, a long time ago. That spacecraft is still moving today. Very fast. It's just now leaving the solar system. There's nothing pushing it. There's no rockets. There's no force pushing it. It's just moving really fast. It's one of the fastest things that humans have ever made. How can it be moving so fast if there's nothing pushing it? Amanda. It was already moving when we launched it into space.
There's nothing stopping it from moving.
And there's no friction in space, right? We live in a world of friction. Everything we do, all the time, there's friction, right? So we say, if I take a book, like this book, and I throw it on the table, it stops, right? And in order to make it move again, I gotta push it, right? So we have this misconception. We have this idea that in order to keep something moving, you have to have a force. But that's only because we live in this world where there's friction in everything we do. And so what really happens is we push it, we get the thing moving, but there's a force acting against the book that slows it down and stops it. If this table had no friction, and I pushed the book, what would happen? It would slide until it went off the table. This plane has zero net force. It is not accelerating. But that does not mean that it's not moving. Let me say that again. There's no net force on the plane. It is not accelerating, but it is moving. Okay, so very, very important, very, very, very important concept in physics. If you don't understand this concept, you'll do very poorly on the forces test. And in the rest of physics too. I'm going to tell it to you right now. Are you ready? Force does not cause motion. Force causes a change in motion. So force does not cause motion. Force causes a change in motion. If you ask 100 people on the street, what does a force do? 99 people will tell you it makes things move. And if the thing starts out at rest, that is true. I need a force to make this move. But I don't need a force to keep it moving. If there's no friction, it will just keep moving. You are on a big ball of rock right now, and it is moving through space with no friction. It goes around the sun at the same speed. It doesn't slow down. And there's nothing pushing it. It just happens to be moving that fast. Madi, you had a question?
Yeah, like if a car goes 60 meters per second, there is no net force, right? But if it start to move like 80 meters per second, it has like net force.
Give him a golf clap. That was good. Okay, so if I'm driving along, this is a really actually interesting question and a good question. If you get in the car and you start, and you put your foot on the gas, and then you kind of like stop speeding up after a while, right? And that's because there's something we don't talk a lot about in Physics 11, but as you drive, as you speed up, the friction pushing against you increases. So when you get to say 40 meters per second, you're gonna have this much friction, right? And then if I put my foot on the gas, it goes more, right? So now I accelerate, I get even faster. But as I get faster, the friction grows again until these two are equal. So you're right, if you travel at a constant velocity of 60, no net force. The push force and the friction force are the same. If you drive at 80, at a constant velocity, these two are the same. But going from 60 to 80, this is bigger than this. I push more, and as I get faster, this grows until I meet that constant velocity again. Does that make sense? Okay. That's a great way to think about it. Okay, inertia. Let's say we go to the go-kart racing track. You know, do you guys know what go-karts are? Somebody had to ask me the other day. It's a teeny little race car that you get in, and you drive around the track. There's 3 times when you will experience inertia. Tell the person beside you the 3 times. If you're racing a car around a track. Anna's got one. Anna, tell me the one you're talking about.
If you stop, your body goes forward, and if you speed up, your body goes backwards.
Good. So if you hammer the gas, you go like this, right? Let me ask you a question though. Are you really, if you hit the gas and you accelerate, are you really moving backwards?
No, you're staying still.
Ah. So your head has what? Inertia. So your head actually stays where it is, but your body gets pulled forward by the car, right? And so you feel like you're being pushed back, but actually you're being pulled forward. Okay, when you hit the brakes, what happens? You go forward, right? But really what's happening is you're moving at a constant velocity and you hit the brakes. And your head has inertia, so it wants to go the same speed. Your body is slowing down, and so you feel like you move forward, but actually your head is moving the same speed, and your body's being slowed down. Ava.
Why does your head only have inertia, not the rest of the body?
Oh, the rest of your body does too, but you are held in your seat, right? With your seatbelt or whatever. Yeah. Have you ever had something in your car, like on the dashboard or something, and you speed up? What happens? It goes backwards, right? But it's just staying where it is, and the car is moving ahead underneath it. Have you ever had to hit the brakes and something goes forward? Hopefully not your coffee. So the thing wants to stay where it is, and if you're moving, it wants to keep moving, and when you hit the brakes, it just keeps moving, right? What about turning? If we're in a car and I yank the wheel this way, what are you gonna do? You're gonna lean that way, right? Okay, this is very important. When you push the wheel, you feel like you lean out. But watch carefully. You don't lean out. Your body gets pulled away from you. So put your hand like this. This is you, put you on the car. You're driving forward and then you turn. And you look like you're leaning over, but actually you just have inertia. And so you're really getting pulled out from underneath. And your body wants to keep going forwards. Okay? Imagine you have a book, and the book sits on the table. Is there a force on the book? Bless you. What's pulling down on the book?
Gravity.
Gravity. Like this, right? Should this be accelerating downwards? Is it? If this is the only force, then the book will accelerate, right? Like, if I removed the table, what would happen to the book? It would fall, right? So what is this missing? Yeah. So there has to be a force pushing up on the book. And as Junior knows, this is called the normal force. You are experiencing it right now. You're in your chair, not accelerating up or down because gravity is pulling down on you, and your chair and the floor and the table is pushing up on you. We call that the normal force. Most people don't know about the normal force. We just think there's just gravity and that's it. But if there was only gravity, we would be accelerating downwards. Right? Put your arm like this, and then this one like this. What do we call this in math? This is parallel. This is perpendicular. In Latin, perpendicular is normal. So the normal force is the perpendicular force. It's always perpendicular to the surface. Okay. The book stays there. It's at rest because its net force is 0, so the acceleration is 0. If I remove the table, this disappears, and then the book falls. So if I hold this up, I'm applying an upward force, it's balanced and 0 acceleration, but if I remove that force, it comes down. Okay, I'm gonna give you some little situations, inertia situations, and I want you to just read it, and then on a separate piece of paper, you're gonna write why there's inertia and how the inertia is involved. Just a couple sentences. If you do those now, you can just take a picture of them and hand them in, and you won't have homework. And I'm also gonna give you